Okay, so where we ended last time was we were talking about how in organic chemistry, the vast majority of reactions that we study fall into this category of being polar reactions. Reactions that take place between an electron-rich nucleophile and an electron-poor electrophile, right? And our nucleophiles attack electrophiles. And then we went through and we made this kind of a list, this little bit of a study guide here for how to recognize nucleophiles. Again, nucleophiles being our electron-rich species. Well, it's super easy to spy nucleophiles that have these net negative charges. These are our strong nucleophiles. But nucleophiles, as long as they have a lone pair that they can donate, they can be nucleophiles. So even if they're neutral, they would be considered weak nucleophiles. But these also work to be nucleophiles because they have these pairs of electrons they can donate, mostly in the form of lone pairs. However, we also have this carbon-carbon double bond, that pi bond, that can play the role of a nucleophile as well, a pair of electrons that can be donated. And so where we left off, and nucleophiles I think are a little bit easier to spy. Electrophiles can be a little bit trickier, but we have these different categories that we're going to learn how to spy. All right, so first of all, the most obvious electrophile being that carbocation, super obvious electron-poor species because it's got that net positive charge, but most importantly, it can accept electrons because our carbocations have incomplete octets. We have acids are also electrophiles. So acids are electrophiles is this key phrase that you want to have in your head. We're going to see acids catalyzing chemical reactions all the time. What's going to happen first is that acid's going to be donating a proton to some nucleophile. It's going to be playing the role of the electrophile at that, specifically at that donatable proton. Okay? And what makes an acid a good donor of that proton is it's got a nice stable conjugate base. In this case, that conjugate base would be water, but as soon as that proton gets plucked off, this thing plays the role of what we call a leaving group. All right, a good leaving group is something that gets kicked off and it itself is nice and stable. It's happy to leave and be all by itself. All right, and that leads us into our next category of electrophiles that we want to be able to spy here. And that is when we see carbon bonded to a good leaving group. All right. So first of all, the quintessential example that you guys know of at this point in your organic chemistry career, and we'll see a few more examples of good leaving groups, but the one that you've been introduced to thus far are our alkyl halides. So if we have an alkyl halide that is an organic molecule that has some halogen on there, this molecule right here is a good electrophile. Okay? Specifically, it's got these two important criteria for being a good electrophile. Number one, it's electron poor, right? And that's because we have this polar bond between bromine and carbon. Carbon being the less electronegative element means that bromine is able to pull all that electron density away from that carbon atom. All right, so we have this polar bond here. Okay, and again, that polar bond is important because it creates that electron-poor carbon. All right, but that's not quite enough. Again, not only does an electrophile have to be electron-poor, it also has to be able to accept a pair of electrons. And that's why the bromine here is so key. We can have some nucleophile come along and attack that partial positive carbon, but I can't stop there because that carbon would be breaking its octet. It can't accept a pair of electrons and then we're done. It has to kick off that leaving group. All right, so the halogen here, our halogens are going to be playing the role of a leaving group. Okay, this reaction here, we would kick off that bromide ion. All right, and again, that's playing the role of our leaving group. Okay, Just to finish this off, in this reaction here, we would now have a new bond between that carbon and our nucleophile. Okay, so this would be a substitution reaction here. Our carbon attacks, our nucleophile attacks that partial positive carbon and kicks off that halogen leaving group. Again, for right now, the only good leaving groups we know are our halogens, so let's just note here, our good leaving groups are our halogens. These are good leaving groups. And that's because whereas most elements don't really like to hold any formal charge, halide ions are particularly stable because those halogens are very electronegative and they just need that one electron to complete their octet. So this guy's got a nice complete octet. It's floating around all by itself. All right, so these are good leaving groups because our halide ions are nice and stable. All right, that's the important key of a good leaving group, is once you kick it off, it's got to be happy, right? If it's going to be very unstable to be kicked off, then it's not going to want to be kicked off. A good example of something that is not going to be an electrophile would be an alcohol. All right, so why isn't an alcohol a good electrophile here? Well, do we have a polar bond in our alcohol? Is oxygen more electronegative than carbon? Yeah, oxygen's the second most electronegative element on the periodic table. It's even more electronegative than bromine. So yes, this is indeed still a very polar bond here. So check, check, we have our carbon that lacks its electron density. The problem is that carbon can't accept any pairs of electrons. If we tried to play this same game where we had some nucleophile do the attacking, we would have to kick off this thing here. All right, and if we kick this off, we're kicking off a hydroxide ion. And this thing here is a bad leaving group. What do we know about hydroxide ions? What are they? Strong bases, right? If you're a strong base, that means that you are not very stable without that hydrogen. That's why you want to pull hydrogens off of things so badly, right? So this is a bad leaving group because this is a strong base, which means even though we have that nice polar bond here, we don't have an electrophile because we can't kick off that alcohol group, that hydroxyl group, as a leaving group, right? So again, those two pieces of those two criteria are really important. Not only do you have to be electron poor, but this one that's a little bit harder to come by is being able to accept a pair of electrons, right? That's what's going to make our good electrophiles. Okay. Again, we'll be introduced to more good leaving groups as we go throughout the course. Another one that's going to be super important for this particular course. We're going to see this over and over and over again. This is a specific functional group or really bond that you guys haven't talked about before, and that is our carbonyl carbons. All right, what do I mean by a carbonyl? Can anybody tell me? Holy hell, we got some work to do this semester, all right? So a carbonyl is a carbon-oxygen double bond, okay? So carbon-oxygen double bond here, this is what we call a carbonyl. Okay, I'll be good and put my lone pairs on my oxygen as well. We have a lot of functional groups that have this carbonyl bond. Aldehydes, ketones, carboxylic acids, esters, acyl halides, amides, all of which share these carbonyl groups. All right? And what we're going to see is carbonyl carbons are really good at playing the role of an electrophile. All right? So first of all, I'm just going to redraw here so we can make some notes. Let's think of those two criteria. Step one was we had to have a lack of electron density. So, do we have a polar bond here? Yes, again, oxygen being the second most electronegative element is pulling electron density away from that carbon. So check, check. We indeed have this lack of electron density on our carbon. All right, but what was that second criteria? So a good leaving group is one way to get around this second criteria. It's one way to meet this second criteria, but the real second criteria here is being able to accept electrons, right? So why can carbonyls accept electrons? They don't have a leaving group per se. They don't have a group of atoms that we kick off, but they can accept electrons because of that pi bond. So what happens, what we're going to see over and over again, is some nucleophile attacks our carbonyl carbon. Again, we can't stop there or we'd be breaking carbon's octet, but we have this pi bond pair of electrons that can be kicked up onto that oxygen atom. All right? So this is sort of a built-in leaving group, quote unquote. It's not technically a leaving group. So we're going to put it in quotations here. Okay? And this is particularly nice for this carbon. It means it can accept a pair of electrons without ever breaking its octet. Right? It can accept this pair of electrons, and then it just gets rid of this other pair by kicking it up onto that more electronegative oxygen. That oxygen's happy to accept that pair of electrons, or not like super happy, but happy enough to accept that pair of electrons because it is the more electronegative element in that bond. All right? I'm just going to move this over here so we can sort of just finish this off here. We'll talk about these arrows. Hopefully this is review, but just to kind of be clear. All right. Now we have that nucleophile attached to that carbon, and our oxygen has accepted that extra pair of electrons. So what am I going to need to finish off this structure here? What am I missing? That formal charge, right? So that oxygen with its 3 lone pairs, we talked about those bonding patterns last class period. We're going to need that negative formal charge. All right, and then the last category, which we will see every once in a while, but we're going to put it down here for completeness. All right, our last category of electrophiles are our halogens. Okay, so by that I mean those diatomic halogens. So for example, and we always, like, fluorine is technically a halogen. We will often omit it from our discussion of halogens. Fluorine's just so tiny and electronegative, it doesn't really behave quite the same as all the other ones. But diatomic chlorine, diatomic bromine, and diatomic iodine, these are also good electrophiles, or decent electrophiles. All right, and this is a little surprising because I think if we just look at these here, we would say, well, there's a lot of lone pairs. These look like they're pretty electron rich here. So what's going on? The halogens are indeed pretty electron rich, and they are very electronegative, but these are also all relatively large atoms, and our halogens have this special property, really that a lot of large atoms share, of being highly polarizable. right, you sort of have unwittingly been taking advantage of this in your organic chemistry lab using dichloromethane as like a go-to solvent because it dissolves a wide range of relatively nonpolar compounds because those halogens are highly polarizable. And what this polarizability means is their electron cloud moves around a lot. So even though these molecules, strictly speaking, would be nonpolar, every single thing up here would be nonpolar, all right? If we looked at an electron cloud on one of these halogen atoms, all right, it's actually moving back and forth quite a bit, all right, to the point where every once in a while it's shifted all the way over, and now all of a sudden that positively charged, whoops, I was doing that in blue. Let me do my electrons in red. All right, our electron cloud has shifted over, leaving that positively charged nucleus more accessible. All right, so we're just going to sort of note here our electron cloud shifts to expose that positively charged nucleus. Cool. All right, so these are, again, it's a little bit harder to, nucleophiles, you can spy pretty easily, especially because they usually just have this net negative charge, making it very obvious. If not, you can spy them as being the more electron-rich species because they got a lot of lone pairs on them. All right, electrophiles can be a little bit harder to spy, but we got these categories that we're looking out for here. Carbocations, acids, carbons with a good leaving group, which is now just alkyl halides, our carbonyl carbons, and this is going to be an enormous one for this semester, and then lastly our halogens. All right, so those are our categories that we're looking out for our electrophiles. So I've been using them a whole bunch, and again, hopefully review, but this is going to be a really important part of this course. So let's go ahead and start talking about these electron pushing arrows. All right, so the whole purpose of these electron pushing arrows are to show the movement of electrons in a chemical reaction. A chemical reaction, we're in organic chemistry, so we're specifically talking about covalent compounds. A chemical reaction is going to be making and breaking covalent bonds, right? That's what we're doing in every chemical reaction that we're talking about. We're making and breaking covalent bonds, which really means we're shuffling around those electrons, right? Shuffling around who's bonded to who. And that's what our electron pushing arrows are going to help us show. Who's bonded to who, right? Or rather, how those electrons are moving in a chemical reaction. If we know a chemical reaction and we know how the electrons move, we call that the reaction mechanism of that reaction. And that's like the holy grail piece of information. That's what we're trying to learn for every chemical reaction, is what that mechanism is. There are some reactions where the mechanism is very well understood. We know exactly how those electrons move. There are other ones where it's still kind of a mystery for us, right? And we're still trying to figure that out. Discovering, or rather proving, a chemical reaction is a very difficult task, and it kind of requires different strategies depending on what reaction it is that you're talking about, all right? What I want to do first is I'm just going to put down an example, and then we'll pick it apart, and then we'll talk about rules for how we draw these things, okay? So first I want to use just like a very simple acid-base reaction going all the way back to general chemistry here. We're going to take this hydroxide ion. We're going to combine it with HCl. All right, and what's our products going to be? Hydroxide and HCl. What's one of my products? Hydroxide we said is a Strong base, hydrochloric acid being acid, all right? So that means the hydroxide ion is going to accept this proton that that acid's donating. So one of my products, water, and my other product, that chloride ion. All right, so as we said, a chemical reaction all about making and breaking bonds. Everybody take a second. Tell me, what bonds are we going to make? What bonds are we going to break in this chemical reaction? All right, who's got one? Who's got a bond that we're going to make in this reaction? Oxygen, hydrogen. We got this new oxygen-hydrogen bond. This is one that we're going to have to make. All right, what's a bond that we're going to have to break in this reaction? The hydrogen-chlorine bond. Cool. Now I want you to pay special attention to the lone pairs. All right, where do we have lone pairs on our reactant side that we don't on our product side? Likewise, where do we have lone pairs on our product side and they're missing on our reactant side? Who's got one? Let's look at our heteroatoms in particular, since that's where our lone pairs live. All right, who sees a lone pair on the left that isn't there on the right? On the oxygen. All right, so here we go. This oxygen right here, it had 3 lone pairs on the left. It's only got 2 on the right, so we're going to lose this lone pair here. All right, what else? Which lone pair did we gain in this reaction? On the chlorine. All right, so my chlorine over here has 3 lone pairs. Over here we got 4 lone pairs. So we're going to have to gain this one. Okay, so my reaction mechanism is going to show all of these actions here. We're going to show the making of this new bond, the breaking of the old bond. We're going to show how that lone pair disappears from that oxygen and how that extra lone pair appears on that chloride. That's what we're going to be doing with our electron pushing arrows. All right, so I'm just going to keep this up here and start a new one. Okay, so my reaction mechanism here, I will show the creation, and actually let me move just to be consistent with where I'm going to draw it. I'm going to take this lone pair. Doesn't really matter which one I chose, all right? But I'm going to create that new oxygen-hydrogen bond with this electron pushing arrow here. What I'm showing is this lone pair is reaching out and grabbing this hydrogen atom. That's what I want you to think about with your electron pushing arrows. You are dragging this pair of electrons from the base all the way to that atom at the head. All right, not only that, but I have to create this new bond, or rather break this bond between hydrogen and chlorine. I'm going to do that using this arrow here. Okay, so this is my bond formation arrow, and this is my bond breaking arrow. All right, not only that, but I've also shown what happens to these lone pairs. My oxygen started out with 3 lone pairs, and over here it only has 2. Well, electrons aren't just going to disappear into thin air. We can't create them out of nothing. So where did this pair of electrons go? it went into, not the chlorine, it went into creating this new oxygen-hydrogen bond. This pair of electrons over here is the same as this pair of electrons here. And that's what I'm demonstrating with my electron pushing arrow. I'm taking this pair of electrons and I'm creating this new bond with it, right? So if I'm going to be consistent with my color coding here, really this should also be highlighted in green. This is this same pair of electrons over here as over here, okay? Likewise, where did this pair of electrons that was in that hydrogen-chlorine covalent bond go? It now became a lone pair, on my chloride ion. Right, so that's what this arrow here is showing, is this lone, or rather this bonding pair of electrons. It used to be shared between hydrogen and chlorine. Now it's jumped up to be only on that chloride ion. So again, if I'm being consistent with my color coding here, that lone pair, that extra lone pair that we gained, well, that's simply that same pair of electrons that I highlighted in red on the left. All right? So when we make a new bond, what we're going to see is we're turning a lone pair into a bonding pair that will create a new covalent bond. And if we're breaking a bond, that means that we're taking a bonding pair of electrons and turning it into a lone pair. All right? So let's go ahead and lay out some rules for our electron pushing arrows. So step one, most important rules for drawing our electron pushing arrows is the direction in which we drew these. So I had to draw these in this particular direction. If I tried to draw it in the reverse direction, it'd be incorrect. All right, so how do I know that I drew it in the correct direction here? All right, importantly, the base of the arrow, or the tail of the arrow, whatever you want to say. This must begin at a pair of electrons. All right, so let's convince ourselves real quick. If we're zooming in just on this step here, my bond formation arrow, the base of my arrow is at this lone pair, right? My base of my arrow has to start at a pair of electrons. Likewise, this arrow, the base of the arrow, is starting at that pair of electrons. So the base of our arrow must be at a pair of electrons. Now that could either be a bonding pair or a lone pair. All right, either one of those is fine, but it has to be at a pair of electrons. Okay? The head of the arrow. All right, the head of the arrow must point at an atom that's accepting that pair of electrons. Okay, so in this example here, my first arrow, what was accepting that pair of electrons? It was that hydrogen atom. That's where the head of my arrow is. What was accepting the pair of electrons for my bond breaking arrow? The chlorine. All right, so that's the atom that's accepting that pair of electrons. Okay, So here is our important rules for drawing our electron pushing arrows. If both of these criteria are not met, the arrow is not drawn correctly. Okay? Now, there's going to be certain patterns of electron pushing arrows that we're going to see over and over again. So now we're going to talk about our patterns of these electron pushing arrows. All right, and we have an example of the two big ones up there. We have bond formation arrows, and we have bond breaking arrows. All right, and our bond formation arrows, they're always going to have this same pattern that we see. We have a lone pair that becomes a bonding pair. All right, so going back up here, we look at our bond formation arrow. We have this lone pair of electrons, and it becomes a bonding pair of electrons in this reaction, right? So that's our bond formation pattern. Lone pairs become bonding pairs. If we look at our bond breaking arrows, it's the exact opposite. Bond breaking arrows, a bonding pair is going to become a lone pair, all right? Again, exact opposite for bond breaking. Our bonding pair becomes a lone pair. Okay? So sort of we're going to break this sort of goal of understanding electron pushing arrows into two sets here. First, I want to make sure that we can follow our electron pushing arrows, and then we'll worry about drawing them in ourselves. All right, so that's what we're going to work on here, is following our electron pushing arrows. Meaning I'm going to draw a structure, I'm going to put in some electron pushing arrows, you're going to tell me which one of these two categories it belongs to, and then draw the product of that step in our mechanism. That's the goal. All right. Okay. So first of all, before I even get going here, and again, I'll put in this arrow, and your job is to follow it, but let's take a step back, and based on what we discussed before, everybody take a second and try to tell me who the nucleophile is and who the electrophile is in this reaction. All right, my nucleophile is what? Electron rich or electron poor? Electron rich. Which one's my electron rich species up here? The HS, and specifically if I asked for what we would call the nucleophilic site, it would be that sulfur atom, right? That specific atom with all that electron density. And my electrophile will be this molecule here. What's my electrophilic site? That positively charged carbon. And what do nucleophiles do to electrophiles? Attack, all right? And so that's what's going to happen here. I'm going to draw in this electron pushing arrow. You're going to tell me whether I just drew a bond breaking or bond formation arrow, and then draw me the product. right, what do we got? Bond breaking or bond formation here? Formation. And what gives it away? I'm starting at that lone pair of electrons, right? So that's how I know that this is going to be a bond formation arrow, which means that lone pair is going to become a bond, a covalent bond. All right? So now I have this new covalent bond between sulfur and carbon. My hydrogen didn't go anywhere, right? It was just that pair of electrons on my sulfur that did my attacking. And so this is my product here. Okay? Charges are a notoriously pain in the butt thing with regard to our electron pushing arrows. Okay? One of the helpful things to keep in mind is this idea of conservation of net charge. My net charge has to be the same in each one of these steps. So what would my net charge be over here on my reactant side? 0. I got my negatively charged hydrogen sulfide ion and my positively charged carbocation, which means my net charge over here better be 0 as well. Okay? So charges are something that's easy to get lost on. So just make note, one kind of easy way to spy whether you're missing a formal charge is keeping in mind this idea of a conservation of net charge. All right, let's do another one. Okay, again, I'm going to put in an electron pushing arrow, and you're going to draw me the product. Actually, first you're going to tell me whether it's bond breaking or bond formation, and then you're going to draw me the product. All right, what do we got? Bond formation or bond breaking? In this case, it's a bond breaking arrow because I'm starting at that pair of that bonding pair of electrons, which means that that bonding pair of electrons is going to become what? A lone pair. And a lone pair where? On that iodine. So now that iodine has 4 lone pairs. My organic molecule here has lost that bond. Boom. And I'm done. No. So what am I missing? The charges. All right. So these are, one of these is a little bit easier to see than the other one. So first of all, my iodine here, what should my formal charge be? -1. We took that bonding pair of electrons and turned it into a lone pair. This was our bonding pattern for a negatively charged halogen. Okay? So now I'm done. No, and this is like the hardest one to see here, all right? And this is why keeping in mind that conservation of net charge is super helpful. Because what's my net charge over here? And so what must my net charge be over here? Which means that I'm missing a positive charge, okay? That positive charge is on that carbon that lost its pair of electrons. This carbon here was super happy just chilling with a complete octet, sharing 8 electrons, and all of a sudden it got that pair of electrons taken from it, right? So now all of a sudden this carbon is left with that incomplete octet, only 3 bonds, meaning it has that formal charge of +1. Carbocations are the hardest to see because we leave hydrogens implied. So this molecule right here, all by itself, isn't like an illegal thing to draw in organic chemistry. It just implies that there's a hydrogen there, but there is no hydrogen there, right? So that's why spying our carbocations is going to be difficult, and keeping in mind that idea of conservation of net charge will help you forget making those mistakes. Okay, and last example here that we're going to do, so again, of following our electron pushing arrows. All right, again, if we're going to try to predict what's going on here, which one's my nucleophile? That oxygen, what gives it away? The negative charge, right? Electrophile is always a little bit harder to spy. This one here is our electrophile. Specifically, what's that electrophilic site? The carbon, because the halogen itself is playing the role of the leaving group, right? So the carbon at the base of that halogen is what's going to be getting attacked here. Cool. So everybody take a second, categorize, this time I put down these 2 arrows, categorize these 2 arrows as being either bond breaking or bond formation, and then draw me the product of this step in my mechanism. All right, so this first arrow here would be which one? Formation or breaking? So this is a formation arrow. And what about this second arrow here? This would be a bond breaking arrow. All right, so let's form that new carbon-oxygen bond. Okay, my lone pair on my oxygen has now become this new carbon-oxygen covalent bond here. I still got my methyl group on the other side of that oxygen, right? I didn't lose that. And what else am I going to need to complete this step in my mechanism? The chlorine. And that chlorine, being on the other side of that bond breaking arrow, has now accepted that extra pair of electrons. So this, what used to be my carbon-chlorine bond, is now a lone pair sitting just on that chlorine. And to finish this off, I'm going to need that formal charge of -1. Notice that my formal charge over here is -1, so my formal charge over here better be -1 as well. Cool. All right. We learned these different bonding patterns. There's one more that I'm going to introduce that's very important. It was actually one of the first reaction mechanisms that you saw last semester. Was when we started with a carbon-carbon double bond. We said that these carbon-carbon double bonds, these pi bonds, play the role of what? Right? They're kind of the odd one in our list of nucleophiles here. Most of our nucleophiles, like most of the electrons that do the attacking, are lone pairs. But these carbon-carbon pi bonds, we got to note, these are also nucleophiles. And that was the very first category of reactions that you would have ever studied last semester, was these carbon-carbon pi bonds playing the role of a nucleophile. All right, I'm going to throw in an electrophile like HBr. How is it obvious that HBr is an electrophile? What category does that fall into? It's an acid, hydrobromic acid, right? So it's going to be an electrophile at that donatable proton. All right, so this is going to be a third bonding pattern that we're going to see. These two are the easiest: bond formation, bond breaking. There's one more where they both happen in one shot. So these are our bond breaking / formation arrows. Okay, this is where we have a bonding pair of electrons that becomes a new bonding pair. So a bond jumps from one pair of atoms to a new pair of atoms, or really just from one. All right. So that would be this arrow here. Would be a bond breaking / formation. Actually, let me make it even more clear. Bond breaking and formation. So specifically, what bond am I breaking? I'm breaking that carbon-carbon pi bond. And what new bond am I making? I'm making a new carbon-hydrogen bond. Okay? Now in this case, I can't stop here. I have to include one more arrow, or I'm going to be violating this hydrogen's octet rule. We also have to put this one in here, which is what type of arrow? This would just be regular old breaking arrow. All right. Again, now I have my new carbon-hydrogen bond. I could pick either one of these carbons here, all right, to create my new bond with. In certain reactions, we're going to learn there's a logic behind which one we pick. In this case, I picked this specific molecule, so it wouldn't matter. So I'm just going to pick the top one. So here's my new carbon-hydrogen bond. And I have that bromine that's accepted that extra pair of electrons. All right, so everybody take a second and fill in what's missing here, which would be formal charges. Try to complete my intermediate here with any missing formal charges. All right, what am I missing? Negative charge on the bromine, so that one hopefully a little bit more obvious because that's just one of our bonding patterns. Any halogen that has 4 lone pairs has a formal charge of -1. And if the bromine's got a negative charge, what else must I be missing? A positive charge. So where's that positive charge going to go? It's on this carbon right here. All right, let me see if I can't illustrate this a little bit better as to why that carbon has a positive formal charge. I'm going to try to animate this here as best I can. All right, so here's my carbon-carbon double bond, right? And this pair of electrons right here is my nucleophilic pair of electrons, okay? So this pair of electrons is going to reach out and attack that hydrogen. Well, what happened to this carbon at the other end of that pair of electrons? This one down here. Well, it goes from having a nice complete octet, and then when this pair of electrons swings out and grabs this oxygen, now it's left with only 6 electrons, right? So again, I broke that carbon's octet, leaving me with that carbocation. Okay, sorry, let's go back up here. So that's why we have a positive charge on that carbon. Okay, and again, very hard to spy carbocations, but I got that conservation of charge rule that's going to help me at least realize I got to have a positive charge somewhere. All right? The other thing that you can always do is just go in and fill in your implied hydrogens. Okay, well now this one has 4, this one only has 3 bonds. All right, well then that carbon has to be that carbocation. Okay, so when in doubt, just start filling in those implied hydrogens. Whoa, where'd we go? All right, now, that was sort of what I wanted to illustrate with that bond breaking / formation arrow, but I think y'all are good at this point, all right? We've got some skills here, so let's see if we can't finish this reaction off by identifying what my nucleophile is and what my electrophile is at this step. What's that nucleophile going to be? That bromide ion, what gives it away? All that negative charge. And what's my electrophile going to be? Obviously the other thing. But specifically, what's my electrophilic site? That carbocation. And so what do nucleophiles do to electrophiles? Let's finish this off by attacking. And again, follow that electron pushing arrow to give me the product of this reaction. Is this a bond breaking or bond formation arrow? This one would be formation, awesome. Now we got a new carbon-bromine bond. Do we have any formal charges to worry about? No, this one's net 0, this one's net 0, this one should be net 0 as well. Cool. All right, so we got the following down. Let's work on the drawing. Okay, and actually before I go on, let me just sort of point out that notice how useful it is in terms of predicting what happens in a chemical reaction to first just step back and find your 2 categories, right? What's playing the role of the nucleophile? what's playing the role of the electrophile. Again, we don't want to have to treat every reaction as memorization. To the extent that we can look at what these reactants are and start to predict what's going to happen. Be like, oh, well, this atom obviously has a lot of electron density. It's going to attack this thing that doesn't. That's how we're going to understand these reactions and not get overloaded with like just trying to memorize a bajillion reactions, right? Memorizing will fail at some point. There's going to be a critical amount where your brain just cannot fit anymore. So understanding is how we're going to get around that, all right? But yes, again, now we're going to work on drawing these electron pushing arrows. So what I'm going to do is I'm going to put down a molecule. We're going to take this alcohol here. We're going to put in some hydronium. And I'm going to draw the next step in this mechanism here. And you're going to fill in the missing electron pushing arrows. All right, and what you need to do is take a look at where we're starting and where we're ending and figure out, do you need to be drawing in a bond formation or a bond breaking arrow, right? Like what's happening in that step? Oh, shit, my bad. I gotta change my acid here. My bad. We need a hydrohalic acid, not hydronium. Okay, sorry. All right, am I making any new bonds in this step? What's my new bond going to be? My oxygen-hydrogen bond. So this bond right here I'm going to have to make, all right? I'm going to make it by taking a lone pair from that oxygen and attacking that hydrogen atom, right? My arrow rather, has to be drawn in that direction where the base is at the pair of electrons and the head is at that hydrogen atom. All right, am I done? No, I'm also going to have to do what? Break that hydrogen-chlorine bond. So I'm going to start at that pair of electrons, that bonding pair, kick it on to that chlorine, all right, to that chloride ion. Cool. All right, so next step here. Generate a carbocation. We still have our chloride ion floating around. Now we also have a water molecule. Let me draw that the normal way. am I making any new bonds? No. There's no new bonds that are created in this reaction, or rather in this step here. Am I breaking any bonds? Yes. And so I'm going to have to break this carbon-oxygen bond. That pair of electrons will go from being a bonding pair of electrons to just a lone pair on that water molecule. All right, and the last step in our mechanism here, I'll give you all $1 million if you can tell me what happens next here. All right, 1,000,000 kudos, how about? All right, so let's just look. What's our nucleophile going to be? That chloride. And what's our electrophile going to be? That carbocation. So the very last step here, nucleophile attacks our electrophile. Boom. Okay. So in our last step here, we still have that water molecule floating around, so we can draw that in just to be good. And now we have that new carbon-chlorine bond. Okay. So this is indeed one of these reactions that we'll learn of our alcohols here. And again, the goal being to draw in those missing electron pushing arrows. Let's see if we can squeeze one more in here. Last electrophile that we haven't taken a look at. Let's look at one of these carbonyls. All right, I'm going to attack this with a cyanide ion. All right, importantly for our cyanide ion, even though both the nitrogen and the carbon have a lone pair, the carbon's the one with that negative formal charge, right? So that's really my nucleophilic site. And this pair of electrons attacks that carbonyl carbon, kicking that up onto our oxygen. Right, so, oh crap, I meant to do the other thing. Anyways, I guess follow these electron pushing arrows. All right, so this first arrow here, bond breaking or bond formation. This one would be bond formation, so I'm going to have a new carbon-carbon bond. And this one right here, bond breaking or bond formation. This is going to be a bond breaking arrow. Okay, so drawing in my intermediate, I'm going to draw that new carbon-carbon bond. And then I'm going to be good and draw in a linear fashion since it's a triple bond, that nitrogen on there. All right, and then I have my oxygen. How many lone pairs is my oxygen going to need? 3 of them, right? So it had 2, but when we did our bond breaking arrow, this pair of electrons now became a lone pair on that oxygen. All right, and we can also see this based on our conservation of net charge. We have a net charge of -1 here. We better have a net charge of -1 over here as well, right? So we have that negatively charged oxygen. I guess just to continue my color coding here, just to be clear, this lone pair on my carbon is now this new carbon-carbon bond. Okay? Now the last step here, I'm going to have to add in some source of proton bonds, so we're going to put in some weak acid, get some hydronium floating around. Okay, and you're going to finish off this mechanism here, putting in any missing electron pushing arrows. All right, if I tell you my product is this alcohol. All right, do we need any bond formation arrows? Yes. All right, what's our new bond going to be between? Let me get rid of my color coding from this previous step so you can see. What new bonds do I need to form? My oxygen-hydrogen bond, right? So this bond right here, that would have been this lone pair, and we're going to reach out, grab that hydrogen. All right. Am I done? What else am I going to need? I do need a bond breaking arrow as well. That hydrogen can't accept that pair of electrons unless it gets rid of the pair on the other side. All right, that's what will create that water molecule. Cool. All right, so that's what you're going to be doing for me this weekend is you're going to be practicing all of your first semester review. Especially these electron pushing arrows are going to be an important part of this course, and it's only going to get more prevalent the further we go. The last unit is particularly mechanism heavy, and we kind of build from there, build up to that. So make sure that you're comfortable with this stuff. If you are having trouble with any of these basics, please let me know. Please come to office hours, all that jazz. I'm currently locked out of my office, so I've been hanging out in the lobby that's on the second floor. So if for whatever reason I'm not in my office, I'm just in that middle part, all right? But I should be rectified by the end of the week. Cool. All right, I will see you all next week.